watching this, we gave everybody else a copy of these notes. Too bad for you. Lots of vocabulary. Concurrent lines. When three or more lines intersect at a point. So when three or more lines intersect at a point, those are all called concurrent lines. So that point in which all three of those lines meet is called a point of concurrency. Okay? A point of concurrency. We have a theorem here, and I don't ever bother to write the names of these theorems in. You see there's no number there. I shouldn't say I don't bother to write the names. If they have a name, I write the name down. But if they don't have a name, I don't bother writing the number because the number doesn't mean anything. It's simply what chapter it is and what number theorem in that chapter this one happened to be. Okay, so from textbook to textbook, author to author, those numbers will change, and they have zero meaning. So what's important about this one is that the perpendicular bisectors of the sides of a triangle are all concurrent at a point that's equidistant from the vertices. The perpendicular bisectors of the sides of a triangle, okay, are all concurrent at a point. That point is called the circumcenter. Okay? That point is called the circumcenter of the triangle, which means the circle is circumscribed about the triangle. So, I'm going to add a page here. I'm going to draw a triangle. Okay? I'm going to construct for you perpendicular bisector. Okay, remember when we do this, you have to pick a distance. If I'm looking at, come on, seriously? If I'm looking at this segment here, this side, okay, I have to pick a distance that's more than halfway. And the line is way more than halfway. And I draw an arc above and below. And I switch sides. And I do the same thing. Okay? And so when I draw that line in there, won't let me put exactly where I want to. I'll cheat a little bit. Okay? So there's my perpendicular bisector to that segment. And that's what we're doing. We're constructing perpendicular bisectors. So if I do the same thing with another one, again, more than halfway, and so that's certainly more than half this distance. I draw an arc above, an arc below. Okay, switch ends. Okay, and again I draw that line. Alright? And I found where those two lines meet, didn't I? Now, if I didn't make any mistakes, I know the third one's going to meet in the same place. Okay? I'm going to go ahead and do the third one real quick. Just to make sure that I don't have any major mistakes here. I'll make my distance just a little bigger so I don't end up being confused on the same arc over there or something. Draw one there. Draw one. Let me go up to this one. The same thing here. find out that all three of them meet right there. Okay? So those are the perpendicular bisectors. We took time a few weeks ago to practice constructing perpendicular bisectors. Meaning all these blue lines are perpendicular and they bisect these sides of the triangle. Okay? Let's go back to this a second. The point in which they all meet are called the circumcenter of the triangle, which means a circle is circumscribed about the triangle. So let's go back. What we're saying is, if I go from that circumcenter right there, so if I can get that in there just right, I go to here, and if I change color so you can see it a little better, looks like I didn't quite start on the point. I'm just a hair bigger, but notice all three vertices of that triangle are on the circle, isn't it? So that circle is circumscribed about, and that's what they mean by circumscribed. It goes around that triangle through all 3 points. Okay? This is an obtuse triangle. If I would have picked an acute triangle, the center of this, the circumcenter, would have definitely been inside my circle, or inside my triangle, I mean. Okay? It would have definitely been inside the triangle. In this case, it wasn't. Alright? So this circle is circumscribed about this triangle. This point here is called the what? Circumcenter. Okay? This is going to be really challenging for you. You're used to writing and being engaged in reading what you're writing. Okay? And I try to go slow so that you have time to think about what you're writing and not just in copy mode. And today you don't have to. So you're going to have to work hard to be engaged and to think about what you're reading and what we're talking about. All right? Now, I think I am. Yeah. So now if we go to the next theorem, it says the bisectors of the angles of a triangle are concurrent. Concurrent means they all meet at the same point, right? So the bisectors of the angles are concurrent at a point that's equidistant from the sides. This point is called the incenter of the triangle, which means the circle is inscribed in the triangle. Okay? It's the incenter, it's inscribed in the triangle. So I'm going to do this one right here. If this was a perfect world, we had lots of time on this, we would practice this kind of stuff. It's not a perfect world, so I'm just going to show you and hope that you agree that's good enough. All right, so here we have a triangle. I made a big triangle this time. Is it acute or obtuse or right? Acute. It appears to be acute, right? Yeah. I should say correct. Correct. So, let me get my compass. Oh, it's not on here. So let me get a compass out. I'm going to remind you how we bisected an angle. We start with any arc, and we go to the vertex of the angle, and we draw an arc. And then we go to, you notice we created then these 2 points, all right? So we go to those 2 points, and we pick an arc that's more than half that distance. That's more than half that distance, isn't it? I'm going to go a lot more because I don't want my arcs out in the middle of what's going on here. So I'm going to go really big. I'm going to draw an arc out here. And then I go down to the bottom intersection. I draw another arc. Okay? And where they intersect out there, is going to be my point that's on my angle bisector. Sorry, I was thinking for a moment how I could tie this into yesterday's all of a sudden instead of focusing on what I was saying. Sorry about that. So then I do the same thing in another one. So I come down here, I pick any arc I want, I go to the other vertex, and I draw an arc, crosses both rays, okay, which gives me these points. And I go to those points, I pick any arc. Okay, I'm going to go way out here again, so it's not in the middle of my triangle. I come over here. I do the same thing. Okay, and then I draw my angle bisector. Okay. Now when I do the same thing for the next one, again, I'm going to come to this point. Anybody remind everybody else why I'm making this so big? Why am I making my arc so big here instead of just, go ahead, Hunter.
So it's not in the triangle.
So it's not in the middle of my triangle where the important stuff's going to be when I'm done. Okay? That's exactly right. That's the only reason. So if I come over here, put that on there and draw the other one, I find the intersection. Problem is, as you can see, I'm not in the middle here, am I? I'm good up here, but I'm not down here, and this board is not. See what's happening? No, it's close. It let me this time. At first it wasn't letting me put it where I wanted to. Alright? So anyway, I get this point right there. Okay, so when I go to draw that circle, this is a little harder. It's because now it's not the vertex I'm matching up on, it's the side. Remember when we constructed before, we can do everything right, and we still can have a little error. And so my error is right here. This should have been not crossing over the mark. It should have just come right to the edge on all of them like it did on these other two. Okay? And so what we're saying is this distance from here to there is going to equal the distance from here to there. It's going equal the distance from here to wherever that was supposed to meet. Okay? These distances should all be exactly the same. And so my circle becomes inside my triangle. So it's inscribed in the triangle. So when I go around the triangle, it's circumscribed. When I'm in the triangle, it's inscribed. Okay? All right. Any questions on the in-center and circumcenter? Okay, a couple more. Median. The median of a triangle is a segment whose endpoints are a vertex and the midpoint of the opposite side. The center is a vertex and the midpoint on the opposite side. To construct this, I'd have to construct a perpendicular bisector to find these midpoints, but then I would ignore the fact that it's perpendicular and I just focus on the midpoint. Okay? So in this rule here, we're saying that H, J, and G are all midpoints of the sides of that triangle. And so when I connect F, this vertex, to H, the midpoint of the opposite side, I get what's called a median. And when I connect this vertex E with G, the midpoint of the opposite side, I get this segment called the median. And when I connect vertex G with the midpoint opposite it, J, that segment is the median. What's special about these, if you have all the medians of a triangle drawn, this here is what's special about it. The medians of the triangle are concurrent at a point. You notice they all meet at C. C is called the centroid. Okay? That point is 2/3 the distance from each vertex. So that means if I know DJ is equal to 12, then that means DC is equal to 2/3 of 12. And 2/3 of 12 is 8. That's correct, it's 8. 3 goes into 12 4 times. 2 times 4 is 8. So DC is 8. How long is CJ going to be then? 4, because 8 plus 4 is 12, which was the distance we said the original median was. Okay? So the special relationship here is always that point, that centroid, breaks all these medians up into 2/3 and 1/3 lengths. From the vertex to the centroid is the 2/3, the longer part of it, and from the centroid to the side, the midpoint, is going to be 1/3 of it. Yeah?
So the medians, like, where they come into the angle, is that always going to be the angle bisector? Because it looks,
Yes.
It is?
Yep, medians, no, I'm sorry, totally no. Sorry, I misspoke. I wasn't hearing you, I heard you, but I answered too quickly. No, they are not the midpoints. They are not the bisectors. This angle and this angle are not necessarily the same. I'm not saying they couldn't be the same, but they're not necessarily. If I had a special triangle, like an isosceles triangle, then one of them would be a bisector, an angle bisector. If I had an equilateral triangle, then all 3 of them would be angle bisectors, but not in this case. Okay? I just have a scalene triangle here, then these angles and these angles are not going to be the same. And neither are these over here. Okay? They do not bisect the angles. The medians, all the medians do is connect a vertex to the opposite side's midpoint. Which makes them easy to find. If you don't have to construct, you can take your ruler and find the 3 midpoints, right? And then draw the lines connecting the vertex to the opposite midpoint. Makes it really easy to find them. Okay? And that center is called the centroid. Alright? A question that they might ask you is, if this length here is 2, CH equals 2, then what is FH?
6.
If CH is 2, then what's FH?
6.
I'm hearing 6 and I'm hearing 4. How long is FC if C is 2?
4.
Yeah, the CH is the short segment, right? This is the longer segment. So this is 1/3 of the total. This is 2/3 of the total. So compared to 1/3, how much is 2/3? Louder? No, I'm just saying in general. If I don't know how long the 1/3 chunk is, just comparing the two segments. If comparing 1/3 and 2/3 together. So compared to 1/3, how long is 2/3? 2 times as long, right? So if the short one is 2, then this is going to be 4, twice as long, right? 2/3 is a 1/3 and another 1/3.
This is Keycheck. Please call extension 101.
That's how we get
Please call
2/3.
extension 101.
And so then FH is going to be 2 plus 4, which is 6. So if they give you 2 of the side, or one of the short segments, it's easier to find the rest of them. Okay? So let me change this and say, what if this distance is 6? Okay? If CE is equal to 6, then what is GE?
9.
Okay, why?
So 6 is 2/3 of 9.
Okay, but some kids don't do that math that quickly. So what's another way of looking at how I can arrange this?
QC is half of CE.
Nice, that's what I'm getting at. If this is 6, then this is half of that, which is 3. Now, all of my students can add 3 and 6 and get 9. Good job, Brandon. Okay? I knew you could do it. I love Fridays. Half-day Fridays don't get any better. Well, they do get better. If today was a payday, it'd be a perfect Friday. All right. So 3, 6, and 9. Okay? Does that make sense to you, Jeff? Okay. I'm seeing not a lot of you writing that stuff down, those examples. I make them up because I could throw X's in there. Okay? All right. Let's move on. The altitude. The altitude of a triangle is perpendicular segment from the vertex to a line containing the opposite side. Altitudes are what we use when we're finding area because we want to know the height of the triangle. Okay? We use altitudes when we're finding area. And so an altitude of a triangle is a perpendicular segment from the vertex to the line containing the opposite side. So in a picture like this one, if I connect that vertex perpendicular to the opposite side, my altitude looks like that. If I have a right triangle, these two sides are perpendicular, so this would be my altitude. Okay? And if my triangle is obtuse, then my altitude might fall outside. You see the green line here? Oh, I grouped that all together, so I can't. The green line here is the extension of that third side. And that's what this means, containing the opposite side. So this segment right here, this side, is all part of this line. And so the altitude goes from the vertex perpendicular to the line containing the opposite side. So those are 3 examples of an altitude. There. The lines The lines that contain the altitudes of a triangle are concurrent. That point of concurrency is called the orthocenter of the triangle. It's called the orthocenter of the triangle. Okay? Sometimes those orthocenters are way out there. Okay? Sometimes they're really hard to find because you've got to draw your perpendicular altitudes a long ways to get them to meet. Okay? Sometimes they meet right in the middle, but sometimes they're way out there. I'm not going to mess with them. To me, there's nothing special that we do with these. We're just talking about points of concurrency today, and this is a point of concurrency, and so it's being mentioned. Hunter?
What's different between the altitude and the perpendicular line? Is there any difference?
The perpendicular bisectors, the first one we did, the circumcenter. Well, in the circumcenter, we used altitudes that were perpendicular, but they also were the bisector of the opposite side. So that might be the case in this triangle, but over here, that certainly doesn't bisect that side, and over here, it doesn't even touch that side. It touches the line containing that side. So the difference between the circumcenter and orthocenter is that the circumcenter is always they're formed by perpendicular bisectors, and when I draw a circle around that circumcenter, all three of the points of my triangle, nice circle, huh? All three of the points of my triangle are going to be on that circle, putting my triangle inside, or my circle around my triangle, okay? All right. Orthocenter, help me review. What's the 4 points of concurrency? Orthocenter. What's the next one?
Centroid.
Centroid,
Circumcenter.
circumcenter, and incenter. Okay, good. Incenter makes a circle inside the triangle. Circumcenter makes a circle around the triangle. Centroid breaks those medians up into 1/3 and 2/3 relationships of the whole median. And orthocenter really has nothing special with it. Okay? Nothing special that we're studying anyway. Okay? So, understand that. Is that it?
Class over?
No, I want you to put your markers, put my markers back in. Oh, let me pause this. Okay. Let me do this. I'm not going to give you your homework today, but Monday we'll take notes on 5-4 and we'll have a little wrap-up assignment on this. Not a ton, but a little